Hi, I'm Colin. In this module, we're going to use Riemann sums to approximate the value of a particular definite integral. This is a challenge question designed for students aiming for a credit or above in the unit. Recall that a definite integral is always a number that represents the signed area under a curve. Now, there are several common ways of approximating numbers. One way is to say that it's roughly equal to another number. For example, we know that the famous irrational number pi can be approximated by 3.141. Another common way is to establish an interval within which the number must reside. That is, establish upper and lower bounds for the number. Here, we're going to show that the following definite integral is bounded above by pi on 3 and bounded below by pi on 6. In other words, although we currently have no idea what this definite integral is, we do know for sure that it can't be any larger than pi on 3 and can't be any smaller than pi on 6. The magic number we're looking for must be somewhere in between these bounds. Firstly, from classes, you should know that the standard way of establishing upper and lower bounds for definite integrals is by using Riemann sums. Now, looking at our integral, we know that if we integrate the function sine x with respect to the variable x from x equals pi on 6 to x equals pi on 2, then this gives us the signed area under the sine curve between x equals pi on 6 and x equals pi on 2. From classes, you know that any integral is always bounded above by its upper Riemann sum, which we'll call u. Here, I'm going to choose just one subdivision. In which case the upper Riemann sum will just be the area of this rectangle here. Now, the area of any rectangle is given by its length, which here will just be the difference of pi on 2 and pi on 6. Times its height, which will just be the function evaluated at pi on 2. Now, pi on 2 minus pi on 6 is just pi on 3, and sine of pi on 2 is just 1. Thus, the upper Riemann sum is just pi on 3. This proves that the integral is bounded above by pi on 3. Now we do something similar with the lower Riemann sum to establish the lower bound. Specifically, we know from classes that any integral is bounded below by its lower Riemann sum, which we'll call L. Once again, I'm going to choose one subdivision here. In which case the lower Riemann sum will just be the area of this rectangle. Now, its length is once again given by the difference of pi on 2 and pi on 6. Times its height, which is equal to the function evaluated at pi on 6 this time. Now, pi on 2 minus pi on 6 is pi on 3 once again, and sine of pi on 6 is a half. Thus, the lower Riemann sum is just pi on 6. This proves that the integral is bounded below by pi on 6. Now that we've proved that the area under the sine curve between x equals pi on 6 and x equals pi on 2 lies somewhere between pi on 6 and pi on 3, it's time to work out the precise area itself. By actually evaluating the integral. As an exercise to hone your integration skills, you should pause the module now and show that this area turns out to be root 3 on 2. Alright, I hope you found that useful. See you next time.